Hello everyone. Today we are going to talk about one of the important theorems in group theory, that is Lagrange's theorem. Okay. So what does this theorem says? So let's start with the statement of the theorem. If G is a finite group and H is a subgroup of G, then order of H divides order of G. And if we write this in shorthand notation, we write this as order of H divides order of G. Okay, so let's start with the proof. Consider A1H, A2H, A3H up to ARH be the distinct left cosets of G. So by distinct means, and these are the only distinct cosets. So what do I mean by that? So what I mean is, if we take B element of G and we say and let B of H be a coset, then B of H is equals to AI of H for some I less than equal to R greater than equal to 1. Okay, that is, from this B of H is equal to any one of these above cosets, right? So that so by statement that B of these A1, A2 up to ARH are the distinct left coset, I mean this. So we'll use this fact. So since these are the distinct left cosets, we can say that G can be written in this form. So in which is nothing but union from I equals to 1 to R AI of H. Okay, so G can be written in this form. Alright, why? Because if we take any element B from G, then that particular B will be in any one of these cosets. If that does not happen, B of H will be another coset different from all the above cosets, that is from A1 to AR, right? And it will contradict our assumption that A1 to AR are the only distinct cosets of G. Fine. So let's go to the argument once again. Why we can write this in our G in this form is, if we take B an element from G, then B has to belong to any one of these cosets. Why? Because if B does not belong to any one of these cosets, B of H will be a coset that will be different from A1H, A2H, A3H up to ARH. Okay, so that will contradict our assumption that A1H, A2H, A3H up to ARH are the only distinct cosets of G. Fine. So because of this particular argument, we say that G can be written in this form. Second, since these A1H, A2H, A3H up to ARH are distinct cosets, by distinct I mean but this particularly. What do I mean by distinct? I mean that A1 of H, AI of H intersection AJ of H is equals to 5 for all ij, that is I ranging from 1 to R, I less than R and J less than R less than 1. Alright, so by distinct I mean this. So now we will use one of the basic set theory arguments to come up with the result that we want to. Okay. So what basic set theory argument we will use is this. So in set theory we know that mod of a union b is nothing but mod of a plus mod of b minus mod of a intersection b. Fine. So we'll use this particular argument of set theory to come up with the order of elements of G, and we'll prove that order of elements of G is divided by the order of H. Order of G is divided by order of H. Alright. So use the set theoretic argument, that is mod of G is nothing but mod of union of I equals to 1 to R AI of H, which is nothing but mod of A1 of H plus mod of A2 of H plus mod of A3 of H up to mod of AR of H minus mod of all intersection terms. Okay, so as all the cosets are distinct, so the intersection terms will be phi, and the number of elements, that is mod of those intersection terms, will be equal to 0. So by that, what do we mean? We mean that this particular term, that is mod of intersection terms, is nothing but equal to 0, because intersections are phi, and if we take the mod of phi, that is equal to 0. So that implies that mod of all the intersection terms will be equal to 0. So this will give our next step, that is mod of G can be written in this form, that is it is nothing but the summation of number of elements in each of the cosets. Right? So now, since H is a subgroup, and we know by our properties of cosets that mod of AI of H is equals to mod of H, that is number of element in a coset is equal to the number of element in that subgroup. So we will use this particular fact in our previous statement, that is this one, and for each A1H, A2H, what we can write, that mod of A1H is equals to mod of H, mod of A2H equals to mod of H, mod of A3H equals to mod of H, that is mod of AIH equals to mod of H. So what we can write is this: mod of G is nothing but summation I equals to 1 to R mod of H, and which is nothing but R times mod of H. These are summing H plus H plus H plus H R times, so that is nothing but R times mod of H. So what do we get from here is mod of G by mod of H is equals to R, where R is some positive integer. Alright, so this implies, this particular statement that we come up to implies that order of G, that is number of element in G, divides the number of element in group. A number of element in H divides the number of element in G. That is, order of G is divided by order of H. Hence, we have proved the Lagrange's theorem that if G is a finite group, then order of a subgroup divides the order of that group. Alright. So I think you understood the proof. It's fairly straightforward. You start with the coset, you distinct coset, you showed that the union of those cosets will be equal to G. You show that, then you use the set theoretic argument and the property of a coset to come up with the desired result. It's very straightforward. I hope you understood the proof, and if you did not understand the proof, put that in the comment section. I will try to resolve it. Okay, bye.